Welcome back to Calculus 2. In our final little talk about differential equations, this may not be the last video, but this is going to be our last topic for the section. We're going to talk about graphical solutions of autonomous differential equations. So what's an autonomous differential equation? Well, it's just a differential equation where your derivative term is just a function of y, and only y. It doesn't have any x's in it. So here's an example I gave you. It's just defined in terms of y squared minus y. For an autonomous differential equation like this, a value of y where the derivative equals 0 is called an equilibrium point, or a rest point. For this autonomous differential equation, it's very easy to find rest points because this is just y times y minus 1. So this has rest points, or equilibrium points, at y equals 0 and y equal 1. So that's one of the things we're going to be doing. We're going to be finding equilibrium points and rest points, but we're also going to be doing what's called phase line analysis. Which, for this, what we do is we're going to make a diagram on the number line where we put all the equilibrium points, and we're going to label how the derivatives behave around it, specifically the first and second derivative. Then we're going to use that diagram to help us graph a bunch of solutions to the differential equations. It's a bit like how we were following the vector fields in the beginning of this unit when we talked about vector fields and slope fields, but this is using the formula given to us by the autonomous differential equation. So let's go back here to our previous slide, and let's show how this would work. So if we got y squared minus y, we already said we had equilibrium points . 1 and 0. So this is y prime. And on, let's see, for negative values, if I plug in a negative y value, this should be a negative, so the y prime would be positive here. In between these two, say you plug in 1/2, this would be positive, this would be negative, so y prime would be less than 0. And then over here, y prime would be greater than 0 again, because, say, plug in 2, positive times positive. Y prime greater than 0. If I look at the second derivative, which the second derivative would just be d squared y dx squared, which would be, let's see, 2y minus 1 times dy dx, because of the chain rule. So it's still going to have basically rest points or critical values the same place this did, but it also has this one. So we have 1, 0. We also have, that'd be 1/2. So if you look at negative numbers, y prime is greater than 0. This would be negative, so the second derivative would be less than 0. In here, in between 0 and 1, this first derivative is less than 0. In between 0 and 1/2, the second derivative, let's see, say you plug in 0.1, this will still be negative. So negative times negative is positive, y double prime greater than 0. Plug in like 0.75, this will be positive, that'll still be negative, so y double prime will be less than 0. And then plug into this will be positive, this will be positive, y double prime greater than 0. So that's a single prime, this is a double prime. Alright, from that, let's go over here and do some graphs. So we know we have this going on, 0, 1, 1/2, 1, greater, less than, greater. And starts less than, then flips. Okay. Y double prime, less than 0, greater than 0, less than 0, greater than 0. So if we make ourselves a line here, let's say this is 1/2. Two, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So that's 1/2. Down here's 0. Yeah, let's make it a little bit better than that. Let's make this 1. Let's make this 1/2. All right then. What does it do? Well, we draw lines at our different places. I'm going to do a dotted line at 1/2. Kind of a wavy line at 1. It's not actually meant to be wavy, but what can you do? And the way these solutions go, I'm going to start down here. Increasing concave down, so like this. As the solutions approach the rest points, they will hug them, like so. Alright, above that, it is decreasing but concave up in here. That means it's also going towards this thing. Now, up here, though, it's concavity change, because it is still decreasing, but concave down. So that's where the rest of this curve came from, like so. Had concavity change at 1/2. And then up here, it's increasing and concave up, so it's coming away. You notice all these curves up here are spiraling out from the rest point at y equal 1. And at y equals 0, all the curves are coming towards it and staying there. This is what's called a stable equilibrium point, and this is unstable. That's unstable equilibrium. Let's do one from the book. This should be very similar. That's the first derivative, so go ahead and try this on your own for a bit, but y minus 2. So it has rest values at y equals 0, and y equals 2. And second derivative. Would be 2y minus 2 times dy dx. So that's 2 y minus 1 dy dx. So our phase line we've got 0. We've got 2. I'm going to make my mark for the second derivative up here, because it's not really a rest point, just an inflection point. But it's worth pointing out regardless. Alright, down here, we'll start over here. Y prime Negatives. Negative times negative is positive. Y prime greater than 0. Y prime. Negative. If I plug in, say, 1, negative and then times positive is negative, so y prime less than 0. And then over here, y prime is going to be greater than 0 because you plug in 3, positive, positive, yep. Then, plug in our second derivative. Our second derivative has this extra point, but we'll start over here. If you plug in a negative number, first derivative is positive. This will be negative, so positive times negative, y double prime is negative. I think we'll flip at all these places, yeah. Because you plug in, say, a 0.5, still negative, but now that's negative, so this is positive. Go over here, plug in, say, 1.75, positive, times negative is negative. And then first derivative is positive, y minus 1 is positive over here, so y double prime greater than 0. It's very similar to the last one then. Honestly, I think I'm just going to make myself a quick and dirty graph here. So there's 0, there's 2, and there's 1. So we know below is increasing concave down, so lots of these. As you're close to 2, let's see, right below 2, you're decreasing, but then you're concave down until you hit that when you're concave up. So, and then up here, increasing concave up. So pretty much the same graph as last time. That's not always going to be the case. We'll look at a different one in the very next problem. I thought about doing a whole nother video for this, but I think we'll stick to one video for this section and do this problem. It's just going to take a while, so if you want to cut off now for a break and come back and finish it later, that's fine. Alright, this is from 14, I believe, from our actual textbook. Yeah, Thomas Calculus. Page 562. So the Fish and Game Department in a certain state is planning to issue hunting permits to control the deer population. It is known that if the deer population falls below a certain level, M, the deer will become extinct. It is also known that if the deer population rises above the carrying capacity of capital M, the population will decrease back to capital M through disease and malnutrition. Discuss the reasonableness of the following model for the growth rate of the deer population as a function of time. So P is the population of deer, and R is a constant. Let's talk first. So, P is the population, M minus P. That is the difference between the carrying capacity, the largest population that can survive indefinitely in the habitat, and the population. So if this is positive, if the carrying capacity is larger, the population, this sign should still be positive. If it's negative, so if the population is larger than the carrying capacity, the rate of change will be negative. That makes sense, that where you have this M minus P, it'll be negative if the population is too large, positive if the population is smaller than the carrying capacity. So this is right. P minus little m. Let's see. So if little m becomes bigger than P, this will be negative, and it means the population will continue to fall. It will become extinct, go down to 0. So that makes sense as well. This will be negative if P gets too tiny. because then there just won't be enough deer left to sustain the population, and the rest of them will just die out. So sure, this constant then is probably a conglomeration of the two constants you would get for multiplying by this and multiplying by this, but it should still be accurate. Since everything's a constant except for p, this is an autonomous differential equation. Explain how this model differs from the logistic model, which is what we usually talk about in a system like this. This is an improvement over exponential functions, which would just be the RP, because most living things that grow exponentially just grow exponentially until they reach their carrying capacity, because we don't have infinite resources. Eventually they're going to reach a maximum population, which if they grow beyond that, they'll have to die out to a certain extent to replenish the resources. So how it differs is because of this idea of an extinction event. If they get below a certain level, they will go extinct. So we have this extra factor. Is it better or worse than the logistic model? I would say it's more accurate in this case, if that's really true. It just depends on your situation. It might be a pretty small number required to maintain the population. Though it might not, it just depends on the situation. I would say it's probably a little bit better just because it incorporates more information. Let's talk about the phase line now. What would the phase line look like? So, when is this going to be 0? Well, when p equals 0, when p equals capital M, or when p equals little m. And I can tell you right away, I bet this one will be a stable, because the population should tend towards its carrying capacity, and this one will be unstable. So let's see that. If I drew phase line with population of 0, population of little m, population of capital M. So if we think about the variable p, or rather p prime, if p is negative, really that doesn't really make sense because you can't really have a negative population, but I'll plug it in here. If p is negative, negative, positive number, negative number, so negative times positive. So this would be increasing, p prime greater than 0. Here, and here, well, p would be positive. We haven't reached this yet, so this would still be negative. This would still be negative, so positive times positive times positive. Yeah, this would be positive because m minus p is positive. Positive times negative, so p prime would be less than 0. On the other side of little m, this would now be positive, this would be positive, and this would be positive, so p prime greater than 0. And on the other side of big M, this would now be negative, this would be positive, and this would be positive, so p prime would be less than 0. So, to show in part C, in part C, show that if p is greater than m for all t, then the limit as t goes to infinity of p of t is m. Well, if you plug in values that are greater than m in here, you will get a negative thing. It must be decreasing everywhere above m. So it can't really it can't really have a limit that's higher than m, because it would have, if you started at that limit, it would still have to decrease from there, and it couldn't if it was at there. So it must decrease towards m if for all t, m is greater than p. Similarly, for part D, what happens if p is less than little m? Well, it's negative, so it must decrease away from the extinction level down to 0, where it's actually stable there. Because it is decreasing for all values greater than 0 and less than little m. This is a quick little extra video. I actually forgot to finish this problem while I was working on it originally. Didn't discuss everything in part E, so let's finish it up really quickly. What are the equilibrium points? Obviously they're at little m, big M, and 0. That's still the same. But explain the dependence of the steady state value of P on the initial values of P. I believe they're actually talking about the steady state being M. So if you're closer to this, you'll actually increase toward it. If you're closer to this, well, that means you'll go down to 0. So it'll affect your function, really, more than anything else. About how many permits should be issued? Well, it kind of depends on how many deer you expect you have. The point would be to get somewhere in this area in number of population of deer, because in this area you won't have them dying out. They'll still be growing towards the carrying capacity. You don't want to get them below this, so around this would be the amount. Chapter 10, we'll start talking about sequences and series, which is probably the biggest topic left in the semester. We still have to talk about polar coordinates and Chapter 11, but I think this is one of the biggest parts of the semester. So it should be a good time. Talk to you then.